thanks everyone. I'm going to go over really a mixture of the two seed projects that we have where we're looking at the development of artificial cochlear systems. And just to acknowledge my collaborators, Wally Grant, Pablo Terrazaga, and Ralph Mueller are collaborators on the program. And this gives you an overview of some of the background and significance in terms of the medical need. But the real question that we're trying to focus on is, can we develop artificial hair cells that mimic the sensitivity and frequency selectivity of natural hair cells that are in the cochlea? And our research objectives for this seed program were to fabricate and test an artificial hair cell. We had had some prior work where we had developed these artificial hair cells on the mesoscale. And so part of our research objectives for this work were to reduce the length scale associated with how big we could make these hair cells, measure the mechanoelectric response and try to understand the physics to a greater deal of accuracy, and then develop a test setup where we took an artificial hair cell system and measured the electrical response to various mechanical inputs. So this is our progress. I want to really highlight the work that Wally Grant's done. Him and his student Miles Dunlap have been great collaborators on this program. But let me show you what this is. This is a picture not of a hair cell. What we're developing here is two droplets. And each one of these droplets has a salt solution in it. And this is a micropipette that pierces the droplet. This is another, it's hard to see, but this is another micropipette. And this droplet is surrounded by a lipid monolayer. And so is this droplet. And then at this interface, it forms an artificial bilayer that's about 5 nanometers thick. And the function of this bilayer is essentially to act as a transducer. And this is what we had demonstrated prior to this work. But this work has really given us a lot better insight into the physics associated with the transduction properties of the bilayer. And what we're just showing here is that we can create these bilayers. One of the goals was to create these bilayers at smaller length scales, and Miles has achieved that. This length scale here, I apologize, I don't have a size, but this bilayer is probably about 30 microns. 30 microns in diameter, and we have made ones that are on the order of about 10 microns in diameter. So we have been able to reduce the size scale of the bilayer. The figure that you're seeing here is a demonstration of the fact that the bilayer area change correlates to the current output generated by the transducer. We had hypothesized this with some of our previous work, but the work that Miles has done has demonstrated that there's a direct correlation. And this blue region that you see here is actually an electrical measurement of the bilayer area. And the green is the blue is the current generated by the bilayer as the area changes. The green is a measurement of the bilayer length from a visual measurement. And so what you can see is that the change in the length of the bilayer, which obviously we could correlate to area change, directly correlates to the current that we're getting out of the bilayer as it's changed dynamically. And so this, I think, verifies our original hypothesis that it's the area change of the bilayer that gives us this current output. And Miles has also done dynamic tests, and this is probably one of the most interesting results that we've come up with to date. You know, with the time that we have, we can't really go into it in detail, but Miles' work, I think, demonstrates there's really different regions of transduction properties in the bilayer. At the low frequencies, maybe below a millihertz or below a hertz, what we're hypothesizing is that the stretching of the bilayer is what's giving us the current generation and giving us the transduction properties. And so essentially, as the bilayer is squished, right, the area changes, and that area change, that variable capacitance due to the area change, is creating the current that we're measuring in the bilayer. What's interesting, though, is at higher frequencies, and this is some results at 75 hertz, if we excite this bilayer at much higher frequencies, what we believe is that the area change, essentially the dynamic response of the area change, it's too fast to create that area change, and the bilayer is flexing and creating essentially a membrane stretching in the bilayer, which is giving rise to the area change, and it's giving rise to our ability to measure current. And what's interesting about that, we didn't show it on here, but we're seeing there's some previous work that had been done 15, 20 years ago that looked at what's called the flexoelectric effect of bilayer membranes. And they predict that when a bilayer is stretching like that, basically bending, you'll get a frequency doubling effect because of that membrane stretching. And what Miles has shown is that we are seeing that frequency doubling effect in the experimental results. And the way you can see that is he excites it at a single frequency, and at low frequencies, we essentially get a current response only at that excitation frequency. At higher frequencies, what you see here is that we get the current response at the excitation frequency. That's what he's calling this solid line. But then at twice the frequency, that's the dashed line, we're also getting a measurable current response. And so our belief is, again, that at high frequencies, because the excitation is so fast, the bilayer doesn't have time to stretch, and it has time to only bend, and it creates that frequency doubling effect. This is our test setup. Which obviously didn't, it's very simple. There should be a lot of nice pictures here of our test setup. I'm sorry, I don't know why they didn't get on here, but
it is nano.
Pardon me?
It is nano.
Yeah, that's right. That's right.
Do you have a Macintosh?
Don,
is it a Macintosh? Do you use a Macintosh?
I probably did, yes.
Yeah, so we're having conversion.
I had the same problem.
Well, please believe me. If the pictures were here, what you'd see is all the nice work that Jeff Travis is doing. What he's done is he's developed a chamber about that big. He's got basically what we're going to have is a chamber where we're going to be able to insert one of our substrates in it with the hair cell in a fluid. He's done the fluid analysis to determine the right fluid properties so that we're matching similar to what you'd see in the cochlea. And what we're going to do is excite a flexible membrane on one side of this chamber. We're going to be able to visually measure the motion of the hair cell. We're going to be able to measure the current output of the hair cell and correlate those properties. And that's going to be able to allow us to find out, translate what Miles did with these droplet interfacial bilayers into a system where we're actually putting a hair cell in a fluid and exciting it through the fluid excitation. And I would expect, he emailed me a couple days ago, he's probably going to start those tests in a couple weeks. And so finally, just to finish up, just to give you, this just summarizes what we talked about earlier. And this actually has changed. We just published a conference paper. We've not submitted any intellectual property. We do have funded projects, 2 funded projects that are related to this, an NSF program. This must have been an old version or something, I apologize. This is about a $300,000 program, and this is about a $3.75 million program where we're looking at more general concepts of how to use these artificial bilayers as transduction elements. Probably the most important relationship is in our AFOSR program. We're actually working with Dr. Sergey Sukarev at the University of Maryland. He's one of the world experts on mechanosensitive channels. And so, in an actual cochlear hair cell, there are mechanosensitive channels that form a feedback loop that allow the hair cell to increase its sensitivity. And so, some of the work that we're doing with AFOSR may be able to impact this because it would allow us to incorporate mechanosensitive channels into these bilayers. And finally, I think what's interesting, unfortunately Wally's not here, but this whole concept of auditory prosthetics is becoming more interesting to the hearing community. Wally just returned from a meeting about 3 weeks ago where there was several sessions on essentially next generation cochlear implants. And one of the main challenges with cochlear implants is the issue of frequency selectivity, which reduces the quality of the hearing for people that have cochlear implants. And so, while of course it's a long way off, auditory prosthetics is something that's very much of interest to the hearing community, and conceptually these concepts could move in that direction, increasing the frequency selectivity of cochlear implants. So with that, thank you again, and I apologize about the pictures, but I'll make sure that you have the right slides.
Oh,
we've got several versions of it, so we'll make sure we
Okay.
find it. But I've got a quick programmatic question for you. So this review that we have, you've probably been to the AFOSR spring review. So you probably see some similarities here. But one of my questions for you is programmatic in nature, and how, one thing I noticed at that review last year was that they have a lot of projects and areas that are relevant to a lot of things that we're doing within our thrusts. Do you see opportunities for us to interface more with folks at the Air Force and on some of these areas, kind of like what you've been very successful working with them?
Well, yeah, and the Air Force just signed a pretty large partnership with the Virginia Tech Applied Research Corporation. So the AFOSR Spring Review actually took place in Virginia Tech Research Center, Arlington, and all of the AFOSR meetings are going to be taking place in our facility from now on. So VTR is working with them very closely, and so that might afford an opportunity for us to be able to tell them more directly about what's going on here with these programs and try to map it. One of VTR's goals of that partnership is to VTR is going to be working on mapping Air Force needs to capabilities out in universities and industries, and so that might again afford an opportunity. What I should do is put you in touch with Tony Van Cherry.
Okay.
Sounds like a mob boss, but he's actually a program manager. And he's the program manager for AFOSR. Program manager for VTR for the AFOSR.
Okay.
Just a technical question.
Sure.
You said doubling of frequency.
Yeah.
Do you see other harmonics too?
Pardon me?
Do you see other harmonics?
We do see other harmonics, but they're
Amplitude
quite
much.
muted. Yeah. And it's interesting because if you look at the theory for what's called the flexoelectric effect, they didn't talk about much about higher harmonics to those responses. Well, but we certainly see them in our
I would imagine
frequency
so.
analysis. Yes.
Hey, Donna, it's absolutely great. I have a quick question. One thing we always lack kind of in our thrust is an understanding of like transport across bilayers, and that's for cellular drug delivery. That's a major issue for us. And as you were speaking, I was thinking to myself, could we think about a proposal, a group of faculty focused on bilayers and constructions of new types of amplifiers? Do you think there's room for that in the scientific engineering world?
I think there is. Interestingly, Sergey, the guy that we're working with in Maryland, he's looking at, he studies mechanosensitive channels and some of the NIH funding that he has. He's using the mechanosensitive channel as a sensor to study the transport of different molecules across the membrane. And his interest is in for drug delivery and uptake.
Yeah, that's exactly what I'm thinking about.
And I think you could use our platform for that. Either one, in the sense that we could use the ones that we do that are encapsulated, or you could, this region right here, you could imagine putting different stuff through these pipettes.
Basically, tailor your interface right there, right?
Yeah, and that interface then could be tailored with different types of phospholipids and
proteins.
Yeah. So we should talk about
That's exciting. Yeah.
Channels and all sorts
Channel,
of
yeah,
things.
that's exciting.
Well, thank you. Thank you for the support.
All right. Last but not least for the Nano Bio Thrust, Ishwar Puri will be talking about some of his work looking at the Materials Genome Initiative. So Ishwar, I'll turn it over to you.
I also have a Mac, so...
That looks good, huh?
Yeah. So, just for the future, PDFs work as well. You can go through, show view, and you still have all this cool stuff. All right, so I only have 3 slides. The thrust of the argument is that can you essentially use heat fluxes to develop logic devices? So if you were to do that, first you'd have to make a transistor. And the concept of a transistor is that it allows the flux to go in one direction. You have to make a diode. The concept of the diode is that you allow the flux to go in one direction. So the idea here is to have a material which has particular genome